Testing, testing. All right, and we're live. Cool. Welcome everyone to another daily dose of LeetCode. I'm looking forward to today. We're going to start off with a nice strong question. Probably one of the most popular questions on LeetCode. Definitely one that you should know how to do. And the cool thing is we're going to go over it iteratively and recursively. Because some of these questions are good to do both ways. And that's exactly what we're going to do with this one. Because some of these questions are good to do both ways. All right. Apologies for my dog. That's exactly what we're going to do with this one. He's fine though. All right. Apologies for my dog. Okay. So let me mute this. All right. So welcome to the stream. Yep. If you like what you see and you enjoy this sort of thing, if you want to be notified of whenever I come back online, make sure you subscribe and also ring that notification bell. It helps me a lot just to reach a wider audience, and it's just good for all of us to grow together. I like taking comments from the community and trying to experiment with different ways to approach problems. So I think it's cool if we just all grow together. So let's get to the questions here. So I'm going to go to algorithms just like I always do. I'm going to go to easy. So yeah, if anyone's watching this for the first time, the way I'm approaching this is I'm literally doing every single question on LeetCode, starting from the easiest all the way to the hardest, making pretty good progress. I think we're sitting at about 125 questions right now. So that's a pretty nice amount of questions that we've done. If you started with me back when I started this almost, a little over 2 weeks ago, you would be sitting at the same place. And I have all those streams recorded and uploaded with easy navigation with chapters and links to all the different questions if you want to go over it with me. All right, so let's start off with a really nice question. We're going to do reverse linked list. Now, we're going to go over this, like I said, both iteratively and recursively. So I think it's worth it for us to get a drawing here because that's truly where we're going to see the value of this question. So I'm going to open up an ExcalaDraw session here. I'm going to clear this part out. And now let's just start drawing some circles that we can use to represent our nodes here. So we'll have this one, we'll have this one, and I'll also make this one right here, right? Like I'll also have this arrow going this, but this can just represent null. Now in each one of these, let's go ahead and enter a number. And now let's think about what it is exactly that we have to do as we're going along, right? At every single point, I think I did this the other day and I kind of liked it. Imagine we had this like runner right here. We know at the end, right, what do we want our end result to be? And that might actually be a good place to start. So let's copy this whole list and let's put this list right under this one. And let's delete all these arrows because really, what is it that we want our end product to be? We want our end product to be a list that looks like this. So if we're doing this iteratively, and this is something that could be a tough question if it's your first time seeing it, but I think if you draw it, it's really where the help comes. Without drawing it, it's going to be hard to do it on your head. So imagine we're sitting right here, right? You might ask yourself, well, when I'm at number 1, obviously my previous one is null, and my next one is 2. I need to change 2 to be pointing to myself. I also need 1 to be pointing to null, right? Because eventually it's just going to be pointing to null. So what if we just did that right away, right? What if that's like the only thing we did right now? So what you could do is you can say, okay, let's take the next pointer of this guy, which is 2, and set its next to myself, which would actually just reverse this and move it like this, right? And then you can say, okay, take the current one that I'm on and then just set that to null, right? That almost kind of gets you halfway there. But now, how do we get to this next one here? We lost that pointer, right? We've already reversed it. Now we have no way of getting there. So really what we should do is before doing that, let me just undo all those changes. What if we had another pointer, or what if we had a set of pointers that helped us sort of go along with all this? Imagine we had 3 pointers. We had a previous and we had a next, right? Now, how is it that we can start doing this? Well, I could say, for example, like let this one right? Let my current dot next equal my previous, which right now it's null, right? So we're gonna effectively lose this pointer. But imagine I remove this, and now I say current dot next is equal to null, right? And then now what if we say something like the current one that I'm on is going to be equal to this next one right here, and then my previous will just be equal to the next one, and then this one will be equal to this one, right? The next pointer we also iterate. And now we keep doing the same thing. Like now this next is equal to the previous. Cool. So we remove this one. We set this next to be equal to previous. We move the current one to the next one, or rather we should move the previous one to the current one, and then the current one to the next one, and then the next one to its next one. And now we do the same thing again here. Now we say for my current one, I want to reverse it. So I can set current dot next to here, move the previous one to here, move the current one to its next, and that's it. Really now, if you think about it, the loop sort of becomes when current is no longer a truthy value. As long as current is not null, we can proceed in our iteration. So what does that thing sort of look like in code? Well, let's start thinking about it. So I think in this question, there's a possibility that we can get 0, right? So we know that if we have an empty head, or if the next is nothing, then we can just return .head. If we have an empty head, or if we have a list with just one node, so insofar as the next being null, then we can just immediately return head, right? Now we can start setting up some of these other pointers. We can say previous is equal to null, let current equal to head, and then let, what's the next one? Yeah, let next, and we don't even have to, we can actually do next in our loop. So we can say while current, let next equals current dot next, right? And now we can say current dot next is equal to previous, previous is equal to current, and current is equal to next. And at the end, we should just be able to return previous. So let's run this and see what we get. 5, 4, 3, 2, 1. So let's go over this again, right? If we undo all of these, something that you need to sort of learn is, how can we explain this better? Like, I used to be a little bit hesitant to be risky. And what does that mean? For example, I used to work with a colleague who almost sort of had this beginner's luck sort of attitude where they would just sort of go for it and try something out. And if it worked, cool. And if not, they would just iterate on it and get something else. Sometimes I think we get too caught up in ourselves and we want to come up with this like perfect solution, or we're afraid of something not being optimized for the get-go. But I think you just have to like try things out. So in this case, you know, like we saw in the first place that I can't just immediately set my current to be null or my previous, else I'm going to lose access to my next. So how can we keep track of the next, or how can we always remember it? Well, we just introduce a new variable, right? So now I can simply do the reversal here. So I can say current.next is going to be equal to my previous, which we start off as null. And now we just start moving the pointers. Previous is equal to current, current is equal to next, next is equal to its next, right? Do the same thing again. Current.next is equal to previous, previous equals next, or sorry, previous equals current, current equals next, and next equals its next. Back where we started now. Current.next is equal to previous, previous equals current, current equals next, right? And now, the next time we enter our loop, we see that current is already null, so now we just return the previous pointer. And that's how you reverse a linked list iteratively. So let's go ahead and try this out. Have I already submitted this one? Okay, 63.81. So that's really good. Off to a great start here. Now let's think about how to do this recursively. I think recursively is, I think it maybe is sort of about the same, but actually, you know what? I want to keep the original list I had. Let's imagine we have this list right here, right? So I'm going to delete this. I'm going to delete these. Now we have this list right here. I'm going to draw a line. I'm going to draw a line here right down the middle. Because think about what happens when we call the reverse function with this first node, right? We're going to need to traverse, or we're going to probably need to do something as we're going through this list. And you might think to yourself, well, I feel like I should go to the end because the last node is the thing that I want to return. So I need to somehow get access to this. Can I sort of do it in place like I did before? We know we're going to be going down the stack, right? Each one of these calls is going to increase our stack or make our stack larger. So by the end, when we are back at the unwind phase, as we're popping everything off, we should ideally be popping off or returning this last node here, because that's going to be the new head of the thing that we want. So let's think about this. It's going to be very similar. We call a reverse function with this list, right? This is the head here. So we say, okay, why don't I now call it again with the next node in my list, which effectively makes it this, right? So you can imagine we have a second stack frame now, and we have a list that looks like this. Then we do the same thing. Now we say, I want to call this function with the next node in my list. So now we get to this point. Now we're here. And now we ask ourselves, am I at the end? How do we know we're at the end? Well, I know I'm at the end because the current node's next is null. Like here, current node's 2.next was 3. Here, current node's 1.next was 2. So we kept traversing. We kept recursing, rather, until we got to the end. Now that we're at the end, we can just we can return 3, right? We can do this, right? And now what do we have? Think about this. This is like a little bit strange to see, but we know this is the new head, right? This is the new head. So what if I said, like at this moment when I return this, I'm back in this stack frame. So I have this thing that's returned from the call that I made down here, but now I'm back here, which means I have access to the node that we returned, and I have access to the original node that was part of this stack frame. So we can do something similar where we say, well, I have access to the 2 and I have access to the 3. What if I made like 2's.next equal myself? So how does that look like? 2's.next is 3, which is this thing, right? They're both pointing to the same 3. 2's.next, which is currently pointing to null. What if I made that actually point to myself? And over here, what would that look like? That would look like just another 2 sort of this way. And then I can say for myself, I just want to point myself to null, right? And now what is it that we return? Now we can just return 3, right? We can return the new node, which is the one that we returned down here. It's the one that we return up here, right? And now we get up here. Now what do we have access to? We're back in this stack frame where we have access to 1. 1 is still pointing to 2, right? And the current list that we're creating is over here on the right side. Still have access to both of these. So what can we do? We can do the same thing. I'll take my current one. I'll set my next to myself. So what does that effectively look like? I'm going to take 2's next is now going to be equal to me. And if we look at this from the right side, it's sort of like doing this, right? And then we say 1.next is going to be equal to null. And from this side, it looks like this. How do we translate this into code? Let's come up with that now. So we say if not head, same base case, right? If not head or not head.next, we just return head. Else we need to get the next node. Next node equals reverse list of head.next. Now when I get the next node, what is it that I want to do? Remember, this one is head, this one is next node. So I say head.next is going to be equal to head, and head.next equals null. Return next node. Right, so here we say head.next, which is 3, .next is equal to the head, to the one I'm currently on. Head.next is equal to null, and then we just return the 3, which is the next node. So let's go ahead and run this. All right, looking good. Let's submit. So it's very important that you learn how to draw these things out. like doing this recursively took me a long time. Okay. But when I drew it out, I really saw the bigger picture and I was able to figure it out right away. One thing to remember is when you're returning next node, right? When we get to the point that when we get to our base case and we return head. So let's say at the end, when I return head here, I'm just drawing these lists on the right to show you what we're building. But this 3 that we returned is the same 3 that 2 was pointing to in this stack frame earlier. Like that's a crucial thing to understand. These are not two new nodes, right? It's the same node. So now we have access to the new thing and we have access to the previous thing, and we can do our pointer manipulation to be able to get the list how it is that we want to get it. Same node. So now we have access to the new thing. Pretty important algorithm to learn. It's not even really about linked lists. It's a very good question on recursion and pointer manipulation. So very important to understand. For both of these, our time complexity will be O of n. Now the space complexity for the first one will be constant, and the space complexity for the recursive one will be O of n because of the internal stack space that we have to, right? Like the stack will grow to be as large as the list is itself. So in this case, iteratively, will save us some more space. Thus, it will make it a more optimal algorithm. 2 great ways to approach this question. Highly recommend going through both of them. If I haven't already added this, let me make sure I liked it and I added it to my list. So that's awesome. Let me make sure we're in the right session. Okay, sweet. Awesome. So let's move on to the next one. The maximum depth of an N-ary tree. This is good. I think, did we give an N-ary tree find its maximum depth? Didn't we solve one that was like this? Oh, I think it wanted us to, given an N-ary tree, find its maximum depth. The maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. It's 3, right? So 1, 2, 3. 1, 2, 3, 4, 5. Okay, 5. So this one for sure, I need to draw it out. It's just really no way around it. I have to draw it out. It's too complicated for me to think about in my head. So let's go ahead and start drawing this one out. We're going to open up Excalidraw again. I'm going to draw the more complex one out because this is a nice sized tree. So let's go for it. It's going to take me a second here, so just bear with me. All right, we have 1. I know we're going to have 4 children. And then let's remove this one. We have 2 for the second one, 1 and then 2. So 2 for the second one, 1 and then 2. So let's start connecting the dots here so we know what we're working with. Oh, we can make this longer, right? Yeah. Okay. 2 for this one, 1 for this one, 2 for this one. All right. 2, 1, 2, and then 1, 1, 7, 8, 9 each have 1. So those are the 3 in the middle here. So bam, bam, bam. Copy these. All right. And then we have a 14 down there, right? It's the third column. Yep. We got a 14 down here. I think this just goes sequentially. So I can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do 11, 12, 13, and 14. Okay, sweet. All right, so let's start thinking about this, right? We have already done a maximum depth question before. The main formula was get the maximum depth of the tree on the left, get the maximum depth on the tree on the right, and then get the max of those and add 1. But let's see now if we can sort of start figuring this out. What I think is going to happen is we're going to say get the maximum depth of all my children and then add 1. So I think every single time, right? Like, let's say we start here and I go to the next one, I increase the depth. I don't have any children, so here I can just return 1. Okay. Then I'll come over here. I'll start doing the same thing. So I feel like I already have sort of an idea in my head of what to do. I kind of want to start drawing it out, because once you sort of figure out, that's the benefit of recursion, right? You're solving small problems and they will sort of take care of themselves as long as you write it out correctly. So I know we have to get the max of all nodes, all child nodes, and return max plus 1. So here we can say if if not root, we can return 0, right? Now we want to say let max. Now is there a way that we can always, what would be a nice way to come up with this? It'd be nice if I can like build an array of this, but I guess we don't really need to. I can always say let max equal I just want to take the max of all of them. Now what can my max be here? If it's just 0, and if I'd say for const child of root.children, right, we want to say max depth of root.child. So if I come over here, I say 1, const child max is 0, then I come down here. This immediately exits because there's nothing. So I can return math.max. Now, would I return math.max here, or can I just return the max plus 1? Let me think about this. Could we just say max equals math.max of max, or max depth of root child? And then here we can just return max plus 1. Wonder if this will work. However, plus 1, plus 1. Okay, let's say we go all the way down. Yeah, this should handle the depth. Let's think about this. Well, let's run it and see what happens. That's always like, well, yeah, it's good. It could be good or bad. 1 or 3. Okay, 1 and 3. So we're off here, but that's fine. Give me 1 second to just turn on the AC in my home. I live in Florida, so it's very hot, so I need to have that AC kicking. Okay. Let's see what we're working with here. Instead of just coming up with some code, let's actually write this out. We start here at 1. Then we come to this one, right? Like, what is the max height of this one, right? There's no children, so here it's just 1. So let's just write 1 here, right? As far as our formula goes, that's how it is. We get here, we go to the next child. Start again here. Max is 0. Let's go to the next child. Or over here, max is 0. So it's this one. This is going to be 1. Come over here, has a child, go in here. Has a child, go in here. No children. This thing just returns 1. Okay. So when we get up here, this thing's just going to be 1, and that's what it's going to return, right? Return max plus 1, because the max here, let's think about this. Return 0. We return 0 for the null node. So max equals math.max of 0 or 0, which is just 0. We return 0 plus 1. So now we're up back in here. We just finished doing all of them. So we say 0, 1, it's 1. So now we return 2 up here. Right here we finished doing all the children. So we do 2 or 0 plus 1, so it's 3. Here we finished all the children. So we say max of my children, which is 3 plus 1. So that's 4. Let's do the same thing over here. Now I feel like I'm not getting, I think what's happening is I'm not always getting the max. Max equals math.max of max or max depth root child plus 1, so that's 3. And the next one's 5. We did what? 1 and 3. So this is 1. Max is 0. For const child of root children, max equals math.max of max, or max depth root child. Okay. Max is 0. Come over here. Return 0. We finish this one, so it's max equals math.max of 0 or 1. Pick 1. Wait. This shouldn't be 1 here, is it? Max equals math.max of max, or max depth root.child. Return max plus 1. This was 0. So we came up here. We did 0 and 0. Okay, that's 0. Then we return 1. It's 1 up here. Okay, so it's one of the children has max equals math.max of 0 or 1 for that one. Now we go to the next one. This should be 2. So we get up here 1, 2. Now when I get to this one, math.max. If we do math.max of this one, it has no children. So we just return 1 here. Math.max of 2 or 1, it's still 2. Come over here. Or do we need to set, I wonder if I need to set, I don't know if that will change anything. Max equals max depth. Like, do we need to do something like new max depth equals max depth of root.child? Oh, wait a second. Wait a second. For const child of root.children, max depth child, and then root. Let's run this. 3 and 3. Okay. Typo. I really have to run this slowly for it to be happy. 3, 5, 3, 5. Okay, that's what I thought. Let's make sure. Okay, I was so sure I had the right answer. So I was a little bit concerned when I saw that it was failing, and it was a simple typo. I was about to go into this whole debugging session, which I suppose for all the viewers, you know, it's good to be watching something like that. I'm just making some things more condensed here. But yeah, let's think about the time complexity here, right? Like we need to go through every single node in this tree. So it's going to be O of n for time complexity. Now, if we think about the height of if you think about the internal stack space, imagine we just have a stack over here, right? We start with 1, then we go to 2, 2 is done, then we go to 3, we go to 6, 6 is done, we go to 7, 11, 14, 14 is done, 11 is done, 7 is done, 3 is done, we go to 4. So the space complexity, the tallest it will ever get is going to be h, where h is just the maximum height. Right? It's never going to be n, where n is the amount of nodes. It's going to be the height of the tree, or the maximum depth of an N-ary tree. Phenomenal question. Going to like this question. I'm going to add it to my list. I think it's awesome. So yeah, I'm getting more into the hang of sort of analyzing trees for space complexity and trying to come up with those formulas. Not formulas, but answers. So that's pretty cool. All right. Build an array with stack operations. Not a good quality question, but we'll figure it out. You're given an array target and an integer n, and each iteration you will read a number from list. Build the target array using the following operations: push, push and pop. Return a list of the operations needed to build target. So target is 1, 3, and n is 3. And integer n, you will read a number from list 1, 2, 3 to n. Okay. Oh, and we want to build target. I see. So 1, 2, 3, we push, push, push. We want to get to 1 and 2, and we have 1, 2, 3, 4. Let's think about this. Here we have 1, 2, 3, 4. How is it that we can get? Well, I guess these are the numbers that we have at our disposal. So how would we? How can we come up with this one here? 1 and 2. And here we want to get to 1. Let's do 1 and 3. This one's a little bit more interesting, I feel like. Okay, so I want to get to 3. So let's see. 1, 2. As I'm going through this, right? I start at number 1. And that's the first thing in my target. So I should probably push that one. Then I get to 2. But that doesn't match the current thing in my target, so I pop. Then I get to 3, and it matches the next thing in my target, so it's fine. So what if we had 1, 3, 5, and we had 1, 2, 3, 4, 5. So I think what we can do is we can have 2 indices. I think we can have 2 indices, like an I, or I'll make this I, I'll make this J. So imagine we're just starting off, right? Remember that we said we only push if they're like equal. So this is my target, I'm at the first one. So the first one's equal to my current place in the target. So I'll just go ahead and push that one. And now I'll push this and push this. Not push, increment and increment. This is not the same. Wait a second, it's not the same, so I just shouldn't push it. Then I get to the next one. Oh, but it wants me to. I can't do push, pop, push, pop. Push 1, push 2, pop 2, and push. Push, push. I think it's just always going to be push, pop. Right? Let's think about this. If 2 is not equal to 3, that's fine. We can still push it. Then we increment I. Now they're the same. So should we pop? I think as long as it's not the same, we just do a push pop automatically. I don't even think we have to worry about any other complex logic. We can loop through this one. If it's the same, we push. Right? So loop. We can loop through target. Loop through target. If target of I is equal to n, then we push. Well, if target of I is equal to n, we increment, let's see, increment I, because n is always going to be, else push pop. Push pop. So let's kind of go over this algorithm to see. We have I and j. Target of I is equal to target of j. Increment j. Okay, if target of j here is equal to n, right, we increment j, we push, increment j, push, and now we just get to the next one. It's not equal, so we push, pop, increment I. It is equal. Let's see. It is equal, so we push, push, pop, push. Right? Get to the next one. This goes to the next one. It's not equal, so we push, pop. Get to the next one. Yeah, so I think we just do it while. I guess we can have. Would we have to get to the end? 1, 2, or n equals 4. Let's see. 1 and 2, n equals 4. 1, 2, 3, 4. Let's say here we have I. Here we have j. These are equal, so push. Increment, increment. These are equal, so push. Increment, but j is out of bounds, so you can end. So I think what we can do is we can say let we can say for let I equals to 0, I, and this, do we need to go to n? It goes up to n, right? I less than or equal to n, I plus plus. I can also have let target index equals 0. If target index greater than or equal to target dot length, return result. Let's also create our result. And now we just pretty much do the same thing that we did. So if target of j, if target at target index is equal to n, and I guess we always push, right? We always push, we just don't push if it's not equal to the current one. Yeah, if target, yeah, so let's do result dot push n, or push. If target at target index equals n, target index plus plus, else. Oh, it would be nice if we could, no, yeah, we always push. Let's actually do this first. If target of target index equals end, target index, else result dot push pop, return result. Let's go over everything again. So we have 1, 2, 3, 4, 5, and let's say we have 1, 3, and 5. I starts here. I'll say T for target index, and then we have our result down here. All right, let's go. If target index is greater than or equal to target.length, it's not. So now we can push. Always gonna have that. If target target index equals n, which it does, we increment target. Else result dot push pop. We don't do anything. Now we get to the next one. Okay, first thing we do is push. Okay, if target of target index equal to n, it's not, so we can do pop. Get to the next one. We push. If they're equal, we increase this, go to the next one. Yeah, I think this looks good just from doing a couple of these. Let's run this. Push. Oh wait, let's see, did I change something here? 1 and 3. Oh wait. If target index is greater than or equal to target.length, return result. Return result, because it should break out before target index plus plus target length. It also doesn't want for me to do it. Let me just put it in the right case, because then it looks all weird. The answer here was a little bit longer, so push pop, push pop, push pop, push pop. Okay, we're all over the place here. Let's see why that is. 1 and 3, and my input is 3. Okay, that's definitely going to be an issue there. Push pop, push pop, push pop. It's still going back and forth. Let's see why that's the case, because we always push, push pop, push, right? Target index. If target of target index, so 1 is equal to 1. Okay. We have 1, 2, 3, and we have 1 and 3. Oh, wait a second. This should be 0. And where do we get n from? I don't know why I did that. This should be I plus 1. Push, push, pop, push. Okay, cool. So I was comparing it to n. Let's see what the next answers are here. Okay, push, push. Let's run it and see what happens. Okay, cool. So some mistakes that I made were I was comparing this to n. I'm not even sure. Yeah, n is always going to be the last number. I'm not taking into account when I mean the last number, I mean that n is going to be this, but I'm not taking into account the intermediary numbers, which is my I. I need to do I plus 1 because even though we're using 0 to index into the array, we need to do I plus 1 because that's the one that we're matching against. So I don't think this question is necessarily bad. It's not by any means the highest quality question, but I think it's fine. I'm happy with it. I like my answer. Let's think about the time and space complexity. So 89.8, so we're getting pretty good percentages here. So our time, let's see, we're gonna go through n. So this is bounded by n. Like worst case, it can just go all the way to the end. If this is like 1, 3, 5 and end is 5, we'll have to go all the way. So it'll be linear time complexity. And our space complexity, let's see. It could just be like this is push, push, push. This is push, push. I mean, on average, it looks like it's going to trend toward linear. So we'll be saying that our space complexity here is linear, because for like it's 1, 2, 3 here, and it's 1, 2. Like if all the numbers are incrementing, then our space will just be equal to n. Now, if we have this sort of space in the middle here, then we'll need the extra pop. But I don't think we need to account because we might have like a fixed, not a fixed number, but like some constant of pops. That doesn't really affect the overall space complexity. So I think we can just say it's linear in this case. All right. We did this one, maximum number of words that you can type. I feel like we went over this one yesterday, but let's see. There is a malfunctioning keyboard where some letter keys do not work. All other keys on the keyboard work properly. Given a string text of words separated by a single space, no leading or trailing spaces, and a string broken letters of all distinct letter keys that are broken, return the number of words in text you can fully type using this keyboard. All right. Hello world, broken letters is AD. LeetCode, broken letters is LT. We cannot type leet. Okay. The number of words. Okay, so hello and then world. Okay, so for each one of these words, let's think about this. Or I guess really what we can do is if any of these letters show up in the list of broken keys, we just go to the next word. Now, there's a couple, I mean, are there ever going to be leading or trailing spaces? Distinct lowercase English letters. What we could do so we can actually create an array, call it alphabet as always. Const alphabet is new array of 26. We'll fill this up with 0. We can say for const car of broken letters, we can say the index is car.car code at 0 minus 97, normalizing it to be able to put the letter in the index. And here we can say alphabet at index plus or equals to 1. Now I think what we could do now, like let's think about this is going to be constant space complexity. Well, we can think about that at the end, but just trying to, why am I not making this a set, right? Because a set will grow, the size of the set will grow linearly with the size of broken letters, whereas in this case it doesn't matter the size of broken letters, it can always just fit into this alphabet. It will always be size 26 instead of n of space complexity. So now what we can do is we're gonna need to split this string. I mean that's gonna make this way easier, right? we can really say const split text equals text dot split by space. And now what do we want to say? So let typed equals 0 for const word of split text. And then we can also say for const car of word. So if let's get our code, right? Const code, or let's say const index equals car code at 0 minus 97 if alphabet at index is greater than 0. Now we don't want to, no, yeah, we can break here for const car of word, but then at the end, if I break and then I go to the end, that's not going to be good. So I need to, let's think about this. I don't want to go through all the words. I want to be able to break out of them early. How many of these, for each one of these words, you know what I can also create? I can create a function for this. Can be typed. Can be typed, takes in a word, goes through each one for const car of word, const index equals the same thing, right? Same thing here. If alphabet of index greater than 0, we'll return false, else we return true, right? And now instead of even having this split text word, I can return split text dot reduce. This will be my word. Let's come over here and do this. Here I can say, I can remove this. I see for each one I can say const can be typed equals, oh no, wait. Typed equals can be typed with word. We can return typed equals to 1, ACK plus 1, or ACK plus 0. Return typed equals, actually no, if typed, we can just return ACK plus 1 or ACK plus 0. Let's run this. One and one. 110, 110, let's submit it. 98.17, wow, really happy with that. So let's like quickly start here in the beginning, right? If I were to create a set, I know that to create a set, I'm gonna need to go through all of the characters inside of broken letters. Broken letters can sometimes be 2 characters, it can sometimes be 10 characters, so that set will grow linearly depending on the size of broken letters. But if we make this a fixed size array, it's always gonna be constant space, it won't be linear, right? So if we think about the time complexity here, this right here to create in a new array, I would say this is constant time complexity, right? It's always going to be 26. It doesn't change based on the input. So let's say this first piece is constant. For const car of broken letters, now for us to actually get, for us to get the individual frequencies, then we'll do O of N. Or let's do O of B, where B is the broken letters, right? O of B. Let's write this stuff down. O of 1, this will be O of B. Text.split. I suppose this can be like O of W, where W is the amount of words. Now I think split really ends up being N, so that's fine. let's say O of t, where t is the size of text. Const can be typed word for const char of word, right? Let's say this is O of w, where w is the size of the word in the worst case, right? So split text, we got a lot of different things going on here. For each t in split text, for each text in split text, we're going to be doing a can be typed operation, right? So it's t times w. T times w, and this we're only going to do one. So here, I guess it's going to be like, yeah, m by n, right? So we do n, we do one of those. The other one, we do another one of those. So it's going to be a t times w, where t is the text and text split, and w is this can be typed function. Now the space complexity, again, this is constant up here. Then we have linear space complexity to create the text split. So this will already be an O of n. So based on that, I'm okay with saying space complexity is linear, and our time complexity will be t of w. Hash set or array. Set the original hash set below. Equals true if c 0, count equals 0, count equals 0, else broken. Again, not really sure what this person's doing. New word starts from here. If car is present in ch, then just increment the count. Yeah, I mean, there. You know what? We can actually get away without even doing the split, really, and just keep track of the different spaces. That would probably help us a little bit. But I'm happy with the percentage here, so I think this could be a good solution to present. But yeah, a lot of times, a lot of questions depend on doing something with individual words. And I feel like for that, there's always two cases. We can go by doing the split, or we can just keep track of spaces and do our pointer arithmetic that way. Cool. Let's get to the next one. Short. Ooh, this one is so good. This one's good, man. This one's real good here. This one's really good here. Now I'm wondering. Okay, so given a string s and a character c that occurs in s, return an array of integers answer where answer.length equals s.length, and answer I is the distance from index I to the closest occurrence of character c in s. Right, so in this position, we're 3 away from e. We start going closer, start going closer, start going closer, and then we're here. It'd be nice if, like, let's think about this, right? When we're deciding, and this is going to sound obvious, but I think it's helpful. At any point, it'd be nice if we already had an array of two different distances. Like at any given point, we knew where the next one to the right was, and we knew where the next one to the left was. If that's something that we can figure out ahead of time, that would help us tremendously. So let us, I mean, we really just got to draw it out and think about it. Love LeetCode. How do we start with this? Like the only way, okay, if I wanted to come up with this array, right, the only way for me to know is like I need to know where my e's are. I think I just need to know where the different e's are in here. 0, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. So 3, 5, 6, and 11. 3, 5, 6, and 11. This is where all my different e's are. So at any time, like if I'm here, if I have a 0 here and then I also have the length of the array, like I'm just curious, like if I put a 0 here and then I put 12 over here, would that, let me see if that would help. Let's say we're here, right? But the thing is there's actually not an E there. So I'm going to put L, or I'm going to put E for the next one. And I'm going to start this one off at I. Okay, so here I say is currently I, which is 0. The next, like I look at E currently, right? And there's like three different things that could happen here. Either we're at 0, so 1, E is at 0. 2, E is at, let's just say E dot length, E's dot length minus 1, or E is anywhere else. So we have like three cases here. If E is at 0, then the answer will just be E minus I. 1A E minus I, right? Because 3, 2, 1, 0. If E is at 0, yeah, if E is at 0, then the answer is just E minus I. Because we get here, that's 3. I is 1. So it's 2. I is 2. 3 minus 2 is 1. And now I is 3. So as long we only increment E when it's greater than. So note, I think, increment E when I is greater than E's, wherever E is. Okay, now we get to the next one, and we also increment E. So if it's anywhere else besides both of these, then we can just take the distance between this one, right? Like we take the minimum of the distances on my left or my right. So I'm over here, it's 4. So I can do left is equal to math.abs of I minus E's at E minus 1. And this is just like not very good writing here, but math.abs of I minus E's at E. Right, because now we're at 5, so is it like my current one or the next one? Okay, cool. I do that, I get over here, it's the same thing. And now I come up here and I increment this. Could do the same thing here. And now, let's see, I'm greater than, so I increment. If E, okay, this should be if it's anywhere else. Now if E is at es.length minus 1, I think we can keep just doing, I think we can just keep doing the same thing, because I'll have a left one or the current one. Yeah, so I think we can just do this. Okay, so let's do this. I know I'm getting close to the hour, but I want to see if we can figure this out. So let's say const C locations for const letter of S. No, we need to do I here, right? For let index equals 0, index less than s dot length, index plus plus. If s of index is equal to c, then c locations dot push I. Right? This is gonna tell us where the locations of C are. Okay, now we need let C locations index is equal to 0. And we also get const result. Let result equal this array. Okay, now we need to go let index, again, let index equals 0. Index is less than s dot length, index plus plus. Couple things we could do now, right? We know where C locations is, so we can say if C locations is equal, right? If C locations is equal to 0, what can we do? We can say result dot push we'll do C, not C locations, C locations index. Here we can do push C locations at C locations index minus index. Let's also make sure this I up here is index. Else, we got to get the distances of both. So I say const left distance equals, so I can say const left distance here is either going to be, let's see, C locations as C locations minus 1, const right distance is just going to equal C locations where I currently am, right? Where I currently am. And here we can just result.push math, let's see, math.min of index minus left distance or index minus right distance. Let me close this off a little bit more here. And then at the end, we can say if index is greater than, let's see, if I think I need to do this first actually. If the current index is greater than wherever the C locations index is, we should increase C locations index. And then we can return result. Let us try this out. So I'm going to run this just to see what we got here. Okay, we got some negatives. That's fine. 3, 2, 1, 0. And now we got to figure out why we got those negatives. Probably something really dumb I did here. Left distance C locations of C locations index minus 1 or C locations. Okay, I already see the issue. These need to be absolute values, right? So let's do math.abs. Let's try this out. Really? Still, wait a second. Math.absolute value of index minus left distance. Index minus. Okay. I'm not convinced that something's up here, but let's see. All right, so we have C locations. Let index is 0, index less than s dot length. If s of index equals C, and C locations dot push index. Okay. So let's imagine we're starting off with this one here, right? We said it's 0, 1, 2, 3, 5, 6, and 11. So 1 or 3, 5, 6, and 11. And then we have results, and we have C index here. All right, let index equals 0. Index is less than s dot length. We're also going to have this guy in here, and this will be our I. Okay. So if I is greater than C locations at C locations index, which is 0, right? So that's 3. I is not greater than that. We also did not remember to increment this. Is that going to be the reason? Let's see. Okay. Let's do the next one. All right. Is this going to run? Oh, man. So close. I was so excited. I was like, I got this. I finally got this question. Okay, we're looking for B and we only have 1. So let's try our algorithm with this one. looking for B, 0, 1. We have 1 at 2. And this is AA, BA. Okay. Only got 2. So that's going to be interesting. Because when we get to the next one, let's see, should I ever increment it if we're already at the end? If index is greater than C locations at C locations index, let's see, I'm curious. We're going to have like 2 conditions here. And we'll actually check the first one, right? If C locations index is already at the end, is equal to C locations dot length minus 1. If it's not equal to C locations minus 1 and that one, C locations index plus plus. Let's run this. Okay, well, it still works fine for that one, right? Let's just do this guy here. Because what's happening is I'm going out of bounds, but I shouldn't be. Oh, that hurts. That hurts. Let's try it out. Let's try it out. Okay, if C locations index is not equal to C dot length minus 1, which it is, right? Okay, if C locations index is 0, then we can push 2 minus 0, which is 2. Okay, that's fine. Now we go to the next one, which is 1. It's not 0, so we get the left distance, which is C locations of, ooh, interesting. No, wait, it's always 0, right? We just push 2 minus 1, which is 1. If C locations index is 0, it still is. We do 0. Now the whole time we got to the B, but that's fine. Now we get to the A. So C locations index is 0. Result dot push locations index to minus the index, which is 1. Should this also, does this also need to be the absolute value? This should also be the absolute value. So let's run this. All right, let's go, let's go, let's see. Let's go, yes. Wow, man. I'm telling you, I have never gotten this question before. I've literally never completed this question before. This is how I know, and I truly hope there's people watching, because I want you all to get better with me. There is light at the end of the tunnel, and this is it. This is how I know. I never completed this question before, and this is it. What's the solution say? Minimum array? Ton of stuff here. Math.min. Right? Solution. Boom, boom, boom. Oh, man. That makes me really happy. That makes me really happy. That's awesome. And there, you know what? There might be even something that I can do that I don't even have to work. Like, it'd be nice if we can just always do this. Maybe the left distance is just, if it's 0, let's see, C locations. Like, my left distance is either going to be C locations of index minus 1, or just C locations of 0, right? Because in the beginning, if the left was 0 and the right was 3, we picked 3. we push the index 0. No, that might mess things up. But I feel like there's maybe something better that we can do in here. We probably don't need to be checking specifically for 0, but it'll help me out. Nice. Man, that's a great way to end the stream. Awesome. Well, everyone, if you liked what you saw today, you're interested in pursuing this goal with me, you want to get to do LeetCode problems, let's see, I think we did a nice amount today. We started off at 125. We did at least 530, 130. Let's go. Let's go. 130. Nice. If you want to join in with me, make sure you subscribe to the channel. Ring that notification bell. It helps me a lot just with getting some more reach out there and helping you all get better with LeetCode. And let's keep it up. I think we're doing awesome. You know, I mean, this is the most amount of LeetCode questions I've ever done. I don't care that they're easy. I don't think you should either. It's an accomplishment in and of itself. Let's just make this a movement. Let's make this fun. Let's get everyone on board. Thank you all so much for watching. You all have a great rest of your Thursday and happy coding.